Okay, hi everyone. Sorry for the delay. My computer wouldn't work. I have to switch computers. So, all right. How did the practice problem go? Please, do you have any questions? Get started. You can put them on chat or just unmute yourself and tell me if you had any difficulties with the practice. Go ahead. Okay. All right. So if we don't have any questions, so we can get going. Number 13, 2.4, we look at that. Number 13. Okay, so it tells me the following. We have two sets. We don't know much about them. We know that the cardinality of the set A is M. It means M has an M element and B has an element. And the question is, number 13 is the following. Find the cardinality of the power of A. 1, 2, 3, 1, 2, 3. All right, any ideas how we can do that? I mean, it looks hard, but okay, anybody got anything here? Anyone has any ideas? Okay.
Yeah, I got
I'm listening.
2 to the power 2 to the power 2 to the power m. Yeah.
Right? Is she correct? Is she correct? Okay, I think she is. Let us start. First, let us remember the following, that the cardinality of the power set of A, where A is anything, is 2 to the power the cardinality of A. Okay, so if I want to find the cardinality of this power set of this whole thing, I need the cardinality of the power set of A. So let's do that first. Okay, but if I need the cardinality of the power set of A, so A is a set, the power of A is another set. So I need the cardinality of the power of A. It's like nested things. And then I'm gonna back my way up. The power set of A has for cardinality 2 to the m. Okay, now the power set of A is a set. That's a set. Its cardinality is 2 to the m. So when I take all its subset, we're going to have 2 to the power 2 to the m. Now, I'm going to back to the first. The power of the power set of A is by itself another set. That's a whole new set. So what's the cardinality of it? So the cardinality of this is going to be 2 to the power, the cardinality of this set here, which is 2 to the power 2. So your classmate was absolutely correct. So it's just like a nested thing. You have in set A, collection of elements. The power set of A is another set whose elements are the subset of A. So then you compute the power of it is another subset whose elements are the subset of the power set of A, and so on and so forth. Okay, any other questions? Very good. So, a very straightforward question for you. And then what you'll be doing today is actually fairly simple. We're gonna go very quickly through all the basic operation on sets. And then once we do that, then we can start talking about logic. So just for my own peace of mind, so suppose I take the power set, a fairly simple question of 1, 2. Now we know how many elements this set should have 4 elements, and very straightforward question. 1 belong to the power set of 2. True, false, because. Quickly. I want a quick answers. Logan? Logan, are you there? Anybody else? Can you guys hear me?
Yes, we can hear you.
Okay. 1 is an element of the power set. True or false?
False, because it would be the set of 1.
Yes, because 1 is not a subset of that. Because what's the definition of an element of the power set? It means it's a subset. It's not, because it's not a subset, it's just an element. All right, very quickly. 1, 2 is an element of the power set. True, false, what's happening? Again. Okay, Logan, are you back with us then? Okay, all right, fine. Okay, 1, 2, I understand now. Okay, true, false, quickly. Rachel?
True.
True. Because?
Because the subset is an element of the power set.
Yeah, that's my question. Is it an element? You told me it is true. Because?
Yes.
Because. I want to always to relate. I mean, I'm really after the definition of the power set. Because. What do you think I'm going to write?
Because it's a subset.
A subset, exactly. That's what really I want you always. So I want you always to think something is an element of the power set. The way you justify it, by justifying it is a subset. That's really what I am after. My last question, I think I've asked it last time, I don't really remember, is a subset of the power set of, let us say, 1, 2, 3. True, false, justify. Remember what I have here. Who say yes, who say true, who say false, justify.
False.
False, because.
The subset of the empty set is not an element of that set.
Because, repeat.
The set of the empty set is not an element of that set, of the power set.
That's correct. But what do I have here? My question is not, is it?
Oh no, that is true, because the empty set is an element.
Exactly.
Yeah,
The whole point, that's no problem. The whole point is to make sure what symbol we're using. So now it is true. Finish your sentence.
Because the empty set is an element of that set.
Because the empty set is an element of the power set. Since it's an element, it means every element in here, this set has one element, so the empty set is an element of the power set. It means that set that consists of it is a subset. So be very careful with what belong an element of, a subset of. All right, so this is just a quick question. Now, as I said, we're going to do the basic operation on set. I think most of you are familiar with. I don't know, but you will go through them very slowly. So basic operations on sets. Whenever we create a new, algebraic object, we operate on them in a way. So the generic object you're working with here are sets. So what can we do with sets? So let's A and B be two sets. It means collection of stuff, no more, no less. Okay. Then we take what we call the union of two sets. What is the union? Okay, so the union of A and B is a new set, is a set, which is we denote by A union B. So it's a new set. We're constructing a new set. It's defined by A union B is defined by the set builder notation. All the x's such that x in A or in B or in both of them. The sentence that eventually I will not need to write, but for now I need to write. So the union is a new set which have everything in A, everything in B in it. And sometimes we use what we call Venn diagram, which I will talk a little bit more about it at the end. So suppose I visualize A as this set, and I visualize B as this set. Sometimes visualize A union B as everything here and here together. That's how we use the Venn diagram. Now, intersection. Again, we have two sets A and B. The intersection of A and B is a new set. That we denote by A intersect B is the following. Again, we're constructing new sets. So A intersect B is all the x, that's by which condition, x in A, an element in A, and x an element in B. Okay, operation on sets. Okay, there are two more operations. We're going to state one now, and then later it's not difference. Difference of sets. Okay, so before I define, the difference, in terms of picture, or what we call Venn diagram, what is the intersection? If this is A and this is B, the intersection is what's in A and B. So this would be the intersection in terms of Venn diagram. Okay, difference. All right, so what's the difference? Suppose again we have two sets A and B. Then the difference denoted by A, the order matter here, is defined by. What's the difference between two sets? So the axis or the element which are in A but not in B. Everything in A and not in B. So in terms of picture, because it's always nice to visualize something, if this is my set A and this is my set B, then A minus B is everything in A, everything here, but avoids B. Everything in A, but not in B. So that's A minus B. All right, so the three operations that you will be using, and you probably, a lot of you may have been using already on sets, are the union, intersection, the difference. Okay, let's take a very simple example. So I'm gonna take, let's say A to be 1, 2, 3, 4. And B to be very straightforward, 3, 4, 6, and whatever. Let me take C minus 1, 1, and 2. Okay, now I will write what I want, and you guys tell me immediately what is the union. So what's the union of A and B? It's a set. I'll put the braces. All right, what are the ends of A union B very quickly?
1, 2, 3, 4, and 6.
1, 2, 3, 4, everything in A, right? And then everything in B. 3, 4 are already there. I had to add 6. A intersect B very quickly. Everything in A and in B. They have to be in both. As simple as that.
3 and 4.
And 4.
3, 4. Yeah, you're right. Okay. Now, what is A minus B? What's in A, but not in B? So that should be here.
1 and 2.
1 and 2. And what is B minus A?
6.
Yeah, they have to be here, but they can't be here. So this is equal to 6. No, so obviously those two things are very, very different from one another. All right. So very good. Now, what else? I can start giving to anything I want, A union C, A minus C, but that's really the idea. It's a very simple idea. Now, let me ask you a question just to practice that. I want you to give me an example. You give me example. A, B. I want you to give me an example of two sets, A and B. Neither one of them is empty. So I don't want this scenario. Okay, and I want A union B to be equal to A. Okay, I'll give you a minute to figure out. So give me two sets, A and B. Neither one is empty. And they are different from each other. Let me add also the simple condition. So I don't want them to be the same. A union B equal B quickly. Sorry, A union B equal A quickly. Okay, either put your example on the chat or just in mute and give me the example if you found one. All right, Logan is giving me the following. I will write what she wrote or he wrote. And 1, 2, 3. Sorry. 1, 2, 3 for A. And 1, 2 for B. Okay. So that's the A, that's the B. Neither one is empty. They are absolutely different from one another. And the union is absolutely 1, 2, 3, which is A. So when can this happen? When can A union B equal to A? Can anybody give me under what condition can this happen? I mean, what can you say about A and B if A union B equal A? B has to be a subset of A. So if A union B equal A, this telling me if you take A, this is A, and you take B, nothing changed, you get A. So B has to be somewhere in here. B has to be a subset of A. As simple as that. All right, another question. Again, I want you to play the same game. Give me an example of two sets that satisfy this condition. And let's see, what do I want? Suppose I want A minus B, okay, equal to A. All right, somebody is giving me A to be 1, 2, 3. What is B?
B 4, 5, 6.
B 4, 5, 6. So what are you trying to make the choice?
Trying to have no element of A appear in the set of B.
Right. So what do we call that? I will introduce the definition. Okay, so he's trying to make sure so that no element in A appear in B. So he wants the intersection of A and B to be equal to what? So he's choosing the intersection to be what? Equal to the empty set. Okay, so definition, what does it, what when we say two sets A and B are called disjoint if their intersection is empty. So if A intersect B is empty, we say that A and B are disjoint set. So disjoint means that the intersection is empty. So we say A and B are disjoint sets. So is he correct though? I mean, I'm talking about that, is he correct? So if I take A, the question that if I take the element of B from A, I still get A. So it means that nothing in B has to be in A. Absolutely correct. And later on in the course, we will prove those facts. But for now, just want a feeling for sets. Right. So we define three operations: union, intersection, and difference. There is one more operation that we define on set, and that's called the complement. Complement. Okay. Now, to define the complement, I need to talk about something called the universal set. Because what is the complement? Suppose I take A to be, let us say, 1, 2. Okay? The complement is everything not in A. That's it is. But when I say everything not in A, where do I want this thing to be? Do I want every integer not in A? Do I want every real number not in A? So to be able to talk about what's not in A, I have to say where I want the thing to be. So this will force us to introduce the idea of a universal set. It means, because when I say it's not in A, I have to tell you where is it. So universal set. Okay. The universal set is usually, it's a set that's given to us. So universal set is basically the set under discussion of all the elements under discussion. Means what is my universe under discussion. And universal set, a lot of time we use the letter U for universe to mean universal set. And it's given to us. Otherwise, you're not gonna invent one. So it's usually given to us. Why I have to bring this up? Because as I said, if I wanna tell you what's not in A, I have to tell you where it is. So in this case then, with this setting, what's the complement of A? The complement of A, that is denoted by, there are different notation depending on the book. The book is using A with a bar, for complement is defined by. The complement of A within my universe U is everything in my universe that is not in A. Okay? So when I want to talk about complement, what's the picture that should go with it? Let me say a word. When I talked about union, I didn't say universe because I don't need universe. Everything in here or in here. The same for intersection and difference. In this case, when I have to complement and I want to give you a visual of it, I first have to draw a universe. So I'm going to call this is my U. And A is a subset of this universe. So sorry, I should say let A be a subset of U. My apology. Be subset of my universe. That's crucial. A is in it. And the complement is everything in my universe that's not in A. Right? So straightforward example as usual. Suppose now my universe is Z, all the integers, and A is 1, 2 within this universe. So what is A complement? Let's list the element of A complement. If my universe is Z, the complement is everything which is in Z, but not in A. So what it is? Everything -1, -2, etc. Everything in Z. And the only thing I'm trying to avoid is 1, 2. So 3, 4, 5, and so on and so forth. So everything except 1, 2. And this is important here, everything in Z that's not in A. Now, I can change my universe. If I tell you U to be Z plus, that's the universe. And A is 1, 2. The complement, is this changing, yes or not? Is the complement changing? What's the complement? Absolutely, because now it's only the positive integers. So I have a totally different complement, and that's the importance of the universe. So I don't have those. So everything, every positive integer, which is not 1 and 2. So now I am totally, I have those, and so on and so forth. Okay, so very different. Even A is the same. Changing the universe will change totally the complement. Yeah, totally the complement. That's why when I talk about complement, I have to tell you what the universe is. If I'm talking about A union, A intersection, A minus B, the universe doesn't really play an important role with that. The last thing we're going to talk about set today is the idea of a Venn diagram. Venn diagram is really nothing more than a way to visualize those operations. So please guys, if I'm going fast or you want to see something, let me know, because I don't see your faces. Usually I rely on your faces in class, but now I don't have that. So please help me out in, with questions. Very well. Now, what's the idea of a Venn diagram? As I say, it's a way to visualize sets sometimes. It helps us. So, as I said, A union B, and we visualize it, everything in A, everything in B. So that's A union B. A intersect C. This is A, this is B, sorry, it's everything in here. And then, so that's the intersection. And then as usual, we have the difference. So these are the basic ones. This is A and this is B. That's the difference. I should have used red. And finally the complement, and that's where I put a universe. A is a subset of my universe, and the complement, everything in here. So these are the basic ones. So this is my A and this is my universe. All right, now let us say I ask you the following. Draw a Venn diagram. Venn, sorry, should be a diagram that represent the following. A union B intersect C. Okay, so there is no complement here, so I don't need to worry about universe. All right, I will do that myself, and then you guys will do a problem yourself. So how do we do that? So it means, so basically, this is set A, B, and C. I'm drawing them without any, so that's A, this is B, and this is C. And the question is actually, shade this region. Shade this region. Okay, how do I shade it? I show you, try to understand it. It is A, union. Union is important. Union, it means what's in here, everything in A is in here. So I totally draw A. Everything in A is in here. And then what do I have to put with it? B intersect C. Okay, what is B? This is my B, and this is C. So I have to add to it again this set. So that's really my shaded region. So that's really the shaded region. Okay. All right, let's do now another one. And then I will give you yourself a problem. So let me get a piece of paper first. Let us do A intersect B union C. Okay. Again, I want you to shade the region that represent A intersect B union C. Now, of course, there is an intersect here, and it changed the picture a little bit. So this is my A, this is my B, and this is my C. A, B, and C. And I want A intersect B union C. Now, easy way to shade those are like this. I want things in A. So I'm gonna do that. So everything in red represent in A. And in B union C. To be able to get the Venn diagram, because it's and, the B union C, I'm gonna shade it in a vertical way. And then what's in common will be the intersection. So this is B and this is C. So I'm gonna shade B union C, but I'm gonna shade it vertically, like that, like that. Okay. And so what is the intersection? The intersection is everything that is shaded horizontally and everything that is shaded vertically. So what is the A intersect B union C? Is going to be that piece right there. Okay, so for the intersection, we take A, we shade it one way, and the other part of the intersection, we shade it in a different way so we can see what is in common. Are you with me? Okay. Now I want you to do that. I want you to give you a small exercise and you guys do it and I'll do it and see if we're getting it correct. So here's the question. I want you to use the Venn diagram to decide if this equality is true or false. So I'm going to give you A union. That's what I did. So B intersect C, that's the one I did. And versus A union B intersect A union C. Okay, I did that. I want you to do this and tell me if those are basically the same set, only using Venn diagram. All right, so 2 minutes for you to do, and then we will check the answers. I didn't get the same. All right, anybody else? Logan, I saw you, yeah? Okay, anybody else? Yeah, we'll discuss. Yeah, I saw it, Logan. Anybody else? Adam, Michael. What are you getting?
I did not get the same.
Did not get the same? Okay. Adam also got different. Okay, let's see. Let us do it together then. Maybe not, I don't know. A union B. A union B, it means A union B, right? I do it, this piece, I'm gonna do it horizontally. Okay, am I right? Okay, A union C. A union C, I'm gonna do it vertically and see what's in common. A union C, that's my C. That's my C. A union C, that's my C. I'm still within C, I'm still within C, I'm still within C. I'm stopping for a second. So what's gonna be the intersection? Everything that is shaded horizontally and everything that's shaded vertically. So let's see which is in common. Everything here. So what do you think? Are they the same, yes or not? What can you say? Peter tells me A. What do you mean by that, Peter? So are they the same, yes or not? What do you think? Yes, I'm getting them the same. So for those of you who draw it, make sure that what went wrong. All right, so the way you draw this, A union B, because there's intersection, you take A union B, and then you take A union C differently, and then you see what's in common. And according to this, they seem to be absolutely equal to one another. All right, I'll give you one more. I was planning only on that. I will take another one and I will see what you guys can do. Let me see. Okay, suppose I take A minus B union C versus A minus B union C. I'm just playing a little bit with parentheses, just again. Can I ask about that last one? Of course. Go ahead. Go ahead. What's your question, Logan? That last one, so with the intersection, yeah, with the intersection, it means you're taking what's in common between them. Okay, so A union B is this whole thing. A union C, everything, even this piece, because that's in C. This is in C, so it's in A union C. In C, that's in A union C because it's in C. Everything in C, and even this piece because it's in A, and this piece. So all this is A union C. All that is A union C. However, A union B is everything here. So here, this piece is not in the set because it's not shaded twice for us now. This is not because it's not shaded twice, but all those are shaded twice. All those will be the intersection. Is it making any sense to you, Logan? Just write on the chat yes or no. All right. Okay. Now I want you to do this one, and then we proceed. I want you to draw that. I want to draw this and check, can we like play with parentheses like that? Yes or not? Okay, so I'm gonna put A myself. I'm gonna put B, and I'm gonna put C. So, and then I'm gonna put A. I'm gonna put B, and I'm gonna put C, just exactly like before. I'm gonna shade either one. So the idea is that, can I move parentheses? Can I really play around? Okay, I give you 2 minutes to look it over and tell me are they the same, yes or not. Can we play with parentheses? Not the same. All right, let's see if Peter is right. A minus B. So it's my A. I'm going to take B away. So I'm going to do this piece. I'm going to do the red. So this is A minus B. Okay. Union C. It means everything in C. Okay, everything in C. All right, everything in C. Sorry. Am I right? I mean, I can do mistakes. Am I right? Agree with me? Very good. Now, A minus B union C. Huh. So to do A minus, it means I am in A, but I'm avoiding B union C. So let us have a look. What's B union C? This is B union C. This is B union C. Okay, so it's A. I'm going to take everything in here. It means this is it. Everything in here. Because that's B union C. I have to remove that away. So I'm left with that. So either the same. Am I right in this one? Are they the same then? Absolutely two different sets. So we cannot really play around with this. So this is A minus B. It means everything in here. I'm plopping C to it. This is A. I'm taking something from it, which is B union C. Okay. All right, I'll finish this with one simple problem. And then we start the logic part. My problem is, I'll give you one, and on the homework practice, I will give you another one. Okay, this is a Venn diagram given to you. And a shaded area is given to you. And what I want you to do is to give me an expression. So it's my question. Following is Venn diagram for expressions involving sets A, B, and C. Write the corresponding expression. So I want you to, the shaded area. Can you give me an expression that represents the shaded area? Can you guys see it well?
Could you do A union C minus B?
I write down what you say and I will work with it. So A union C. I'm listening.
And then minus B?
And the parentheses, be careful. No parentheses, I don't accept now.
Okay, so around A union C is parentheses, then the difference of B.
Right, because as we realize, I just gave you an example to convince you that without parentheses, we're in trouble. So nothing without parentheses. Now, is he right? Is he right? I really don't know. This is A union C. No way on earth. Why not? Why not? My region is the shaded region, right? So if it's in A union C, it means in A union C, it means this is in your set.
Oh yeah, I see. Okay.
This is not in my shaded region. Okay, very good. Keep going. So sorry, I have to get rid of that. Now I want you to keep thinking. Okay, I move my hand. I'm having ideas.
Yeah, I think in the chat they corrected it. Instead of union, it should be the expression with the intersection and then the difference with, so A intersection B or C with parentheses, then difference of B.
Okay, now does it really make sense? Yeah, that's fine. That's fine. We're just practicing this. So that's the way that I look at it. As this is this piece taking away that from it. This oval, whatever shape is, like this ellipse shape, that's A intersect C, but we're taking the B away. And now this would be the absolutely correct. All right? All right, I was planning to give you another example, but I will give it to you as a practice for next time. So for Wednesday, you guys have practice problems along those lines from your book. So any other questions before we move on? Okay, so those are the basic operation on sets that is basically like the ABC language of sets. So we need this language continuously. All right, the other language we need to develop in this course is logic. So section, I think that's 1.5. sorry, it's chapter 3 in your notes. So chapter 3, we're gonna start talk a little bit about logic again, because I need a language that we have to work with. So logic. I'm gonna start with a definition. So what is a statement in math? So when I say a statement in math, what do we need? So definition. Okay. What's a statement? A statement or sometimes a lot of other books use the word proposition. A statement or a proposition is a sentence. Nothing more, nothing less. Is a sentence that is true or false, but not both. Okay, so in math, a statement is nothing more than a sentence which is true or false, but not both. So let me give you a very simple example. The number 2, sorry, is prime. It's a prime number. Is this a statement? It means, is it true or false? Quickly.
True.
True. That's a statement. Because you can give me the answer to it. You can tell me that, yes, this is a statement because it's true. All right, 3 is even. That's a sentence. Is this sentence a statement? It means, is it true or false? Can you just tell me? Okay.
Yes, it's a statement.
It's a statement. It's a false statement, but it is a statement. That's really what I want. It is a statement. So this is a statement. Okay, that's a statement. That's a statement. X plus 2 equal to 5. Is this a statement? No, because you cannot tell me what is true or false. It depends on X, but I'm not giving you any info about X. So is this a statement? Absolutely, that's not a statement. Not a statement. All right, one more, and then we proceed. N, a subset of Z. Is this a statement? Yes or no? Can you tell me if it's true or false, just by looking at it?
You'd say it's true.
It's true, it's absolutely, so that's a statement. Okay, so a statement is a sentence that's true or false. So when I give it to you, it means you have to tell me immediately whether it's true or false, because this is the kind of statement we are interested in math. We want our statement to be true or false, not a lot of fuzziness. Now, we use letters such that, so letters like capital letters, P, Q, R, etc., to denote statement. Sorry, to denote a statement. So what do I mean by that? So we use capital letter to denote statement. So in here, I would write the following. Let capital B represent the statement. 2 is prime. That's how we'll write it. Q, 3 is even. So Q represents the statement. 3 is even. This is not the statement. That's closed. I said let R be a statement. N is subset of C. So that's how we'll write this. Now, to every statement, we will assign a value. We will assign the value T if the statement is true, F if the statement is false. So every statement, because it's a true or false, so it has only 2 values. So to every statement, we're going to assign a value. So to every statement, we assign the value T, if statement true, and F if the statement is false. F if the statement is false. So a statement A has two values. It's characterized by its value. It either has a value T if it's true, and it has the value F if it is false. So with this in mind, we go back to our statement. And this one, 2 is prime. The value it takes is true. 3 is even. It is a statement whose value is F. And a subset of V is a statement which its value is true. So a statement, because our definition has two values, a true or a false value. Now, like when we did with sets, every time we construct a new object, we start combining the objects. So we defined a set, then we talked about the union of two sets, and then we talked about the intersection of two sets. And now we define something called statement, and then we're going to start combining statement in the following way. So compound proposition. Oh, those are to go. So compound proposition. Okay. Or compound statement. The object now is basically we are going to combine statements. So sometimes I write it combining because that's what we are doing. Okay. All right. Suppose I have two statements, P and Q. Let P and Q be two statements. It means P is a sentence which is true or false, and Q is another sentence which is true or false. So each one of them has a value. All right, then we define. First, the first statement the new statement we're going to find is the statement that we call P and Q. So that's a new statement. Okay, denoted by P and Q. Okay, what does it mean to define a statement? It means give its value. What's its value in terms of its component? So denoted by is a statement that is true. So it's a new statement that takes the following value. It's a statement that is true when P and Q are true, and false otherwise. What am I talking about? Okay, so I have two statements. I'm combining them, and I'm constructing a new one that I'm going to call P and Q. What does it mean to define a statement for you? It means tell you its value in terms of the value of the pieces, P and Q. So this new statement is true when P and Q are both true. And it's false otherwise. So to be able to memorize, to understand this, we usually draw a little table. And we're going to call it the truth table. Okay, truth table. What does the truth table tell me? It actually helped me to memorize the value of P and Q. That's P and Q, and that's P and Q. What are the values? Now, let's see what's going on. This tells me that P and Q is true when both are true. But how many values P and Q can take? All right, P, okay, I'll draw this and then you don't have to draw this. P can take two values, true and false. And Q can take two values, true and false. Okay, what's P and Q? P and Q, that's a new one. What am I telling you? It's true when both is true. So if P is true, Q is true, it's true. That's it. And if one is false, this is false, it is false, and it is false. How can we write this in a little table? We write it like that. This is my P. It's either true or false. But if it's true, Q could be true or false. So we have to write two values here. If it's false, Q can be true or false, and this is false. What about P and Q? P and Q is true if both are true. Otherwise, it is a false statement. That's the idea of a truth value. So we take the simple example, and I give you the example. So suppose I take P to be 2s prime, and I take, let us say, Q 3 is odd, so I'm changing a little bit, and I take R, something nonsensical, like Earth is flat. Okay? Now, each one of them is a statement because it has a truth value. P is true, Q is true, R, okay, since we are in the 21st century, R is false. So now, what about my new P and Q? What's P and Q? P and Q reads 2 is prime and 3 is odd. Is this new, true, or false? Okay, what's the definition of P and Q? This one is true. This one is true. It means my new compound proposition is true. Now, what if I take P and R? What does this read? 2 is prime. And the Earth is flat. Okay, what does this mean? Is true or false? This is true. This is false. P and R, my new sentence, is going to be false. Okay, so we have two, unless you are a flat earther. No, not really, I can't be. Okay. So P and Q is absolutely, it's a new statement which follow the following group. Now, we can construct another statement, of course, so that's the P and Q. Now, another statement is P or R. So we're going to construct another one, and I have to tell you when this new one is true and false. So P or Q, denoted by P or, should remind you a little bit the union, P or Q is the following statement. It's a statement that is true when P is true or Q is true or both are true. And it's false, so that's when it is true. False when both are false. Okay, so this is too much writing. That's why we take the this what we call the truth table, because you know mathematicians don't like to write that much. And that's P or Q. So when is it true? And its value depends on its component. So sometimes I call P and Q the component of P or Q. And its value depends on the component. So true, false, true, false. So these are all possible combination of the component. When it is true. If both are true, it's true. If one of them is true, it's true. It's false in one case, one and only, if both are false. So or is true if both are true or one of them is true. So if I go back to my previous example, P 2 prime I think that's what it was. Q, I picked 2 odd. 2 odd, I guess. No, I meant 2 even. And R, the Earth is flat. Okay. So now, P or Q, is it true or false? Is P or Q true or false? Quickly. P is true.
True.
I don't care. True. I don't care about Q. I'm done. P or R?
True.
True. I don't care about R. I know that R is false, but it doesn't matter. If one is one is true, I am done. This is true statement. Okay, so the or is true if one of them is true or both are true. False only in one case. So we combine now proposition in 2 ways with P and Q, P or Q. Now there is also another way we do, but it's not combining. It's something based on what? Negation. Okay. What is the negation? If I have a simple sentence, very simple statement, simple. That's what we're going to do now. Suppose my statement is 2 is prime. The negation is, how can 2 not be prime? So the negation is 2 is not prime. So for a very simple statement, the one that I will be dealing with today only, not next time, to negate 2 is prime, the negation is 2 is not prime. That's the negation for us, at least for today. 2 is even, 2 is not even. Everything but even, which is not even. So what is the negation we define? So suppose P is a statement, of course. So let P be a statement. And it's one, a statement. Then the negation of P and denoted by, now this is like the complement. Book use different notation. Our book is using tilde P. So denote and pronounced noun P. Sometimes it's called not P. Is the negation of P, denoted by this and called not P, is the proposition not P. So is the statement, it's not the case that P. It means it's not the case that P. It means whatever P is, it's not the case as P. So what's going to be its truth value? What's going to be its truth value? So this is P. It could be true or false. Not P will be. If P is true, everything that's not P. If P is false, it's going to be false. Okay, so not P is true when P is false. That's really what characterizes it, is true when P false. And it's false when P is true. Okay. So how to negate simple sentence? That's the very simple example. Okay. So let me go back to my same problem. Suppose my P is 2 is prime. And Q, let us say, the Earth is flat. All right. And PQR 2 strictly less than 3. Okay. So first, what is noun P? For those simple statements, let's write it down. Noun P is 2. Everything that can't be prime 2 is not prime. 2 is prime is true. This is false. Earth is flat. The negation, which is definitely a false statement, the negation, Earth is not flat, which is a true statement. Now, 2 less than 3. What's the negation? So this reads 2 less than 3. What's going to be the negation? All right, I can see the negation is 2 greater than 3. You think he's correct? Absolutely. It's not correct. The negation, it means everything 2 cannot be less than 3. Everything else. What's everything else? Greater or equal to 3. So the negation is everything else, which is 2 greater or equal to 3. That's how we negate everything else. Suppose I ask you this very simple question. And I want you to suppose I tell somebody, so you guys don't know let's see, the color of the wall in my room. Okay, you don't know it. I say the color of the wall is white. Now this statement could be true or false. Then what is non-P? And somebody, a student, tell me the non-P is the color of the wall is black. Is this a correct statement? Is this non-P?
No,
No. Give me a solid reason why not.
because it includes any color that isn't white, which includes black, but not only black.
Yeah. Can both be right? Can both be true? The negation has to be false when the first sentence is true. Is it possible both could be true? Is it possible? Yeah. Suppose the color in my room is pink. No, sorry. Can both be true? The color is white and no, I meant can both be false? My apology. Can both be false? Can both statements be false? Suppose the color in my room is pink. This would be false. And this would be false. So a statement, whenever a statement is false, the negation has to be true. So if somebody negated like this, then we know this is not the negation because both of them can be a false statement. The negation always have to be true for P. So the way you negate in those simple sentences is the color of the wall is not white. Everything but white. The complement, everything else. That's the negation. Everything else. Okay. So with this in mind, we define 3 operations, if you want to call them, on proposition. We combine them. We took P and Q and we negate them. Okay, there is one more that I will talk about next time because it's very important, but I want to make comment about the OR before we move on. So what's my comment about the OR? A very important comment. So inclusive and exclusive OR. Inclusive and exclusive OR. All right. If I take 2 propositions, the way we took them, P or Q is true if P true, Q true, P true, Q false, Q true, P false, and if both P and Q are true. Okay, that's what so it means this OR that I defined, this OR is called the inclusive OR. even though that's the or that we use in math, but sometimes called inclusive or. Inclusive means it contains P and Q are true. Now, in English, a lot of time, the or is not inclusive. So the typical example everybody gives is the following. If you go to the restaurant and you ask, and you want a drink, and the person there asks you, do you want coffee or tea? What do they mean by the or here? Coffee or tea. What this person, the waiter, is telling you.
Like, do you want one or the other, not
Right.
both?
It doesn't tell you if you want both. It tells you, do you want coffee or tea? Not both. So in English, usually when we say the or, we mean this one or this one, but they don't really mean both. So this will motivate another or, which is called the exclusive or. That I tell you we don't use in math, but sometimes use, especially, you know, in CS, I guess in computer science they use it. So what's the exclusive or? The exclusive or, and denoted by the following. P plus Q. So it's a totally different notation. So the exclusive or is true if P is true or Q is true, but not both. So we call this, and that's crucial, but not both. It means the truth table for it will be the following. P, Q, P, exclusive or Q. And that's important to know the difference. So P can take two values, true, and if it takes true, Q can take two of them. Now, if P is false, Q could be true or false. So that's the rule. Now, what's P or Q? If both are true, the exclusive one is false. If one is true, the other one is true, it's true. If both are false, are false. Okay, so it's a very different than the P or Q. Different means it doesn't have the same value. That's what different for us mean in this class. They don't have the same value. The P or Q is true, 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 false. So it's different than the or value. In math, whenever we have or in math, that's the or we mean. So if I tell you 2 is prime or 2 is even, the or is the inclusive or. Exclusive or, it has to be made very clear that we're talking about the exclusive or. But in math, always we have the or. So for example, when I had introduced A union B, okay, I wrote it all the x's such that x in A or x in B or in both. That's how I introduce it. But I think I was redundant. Why I was redundant in this problem? I don't need, if I write or in math, or it means this one or both. So I don't need to write or in both. If I said x in A or x in B, it means either here or in both. So I didn't need to write that, and there is a redundancy. The reason I wrote it because I hadn't introduced the meaning of or in math prior to that. Okay, so the or, we have to be careful with it. It's true if both are true, and there is a different or called the exclusive or that have this as a truth table. Right? So we finish at this note. 2 things. You're going to have some practice for next time, and then I gave you a homework, and your homework is due next Tuesday. It's actually fairly simple, but it's just the goal is to rehash all the info we studied about SET. It will be due on Tuesday, next Tuesday, I think at 11:59 p.m. It means on Wednesday I should have it. All right, I'll talk more about it next time. Okay, any questions before I go? All right, bye-bye guys. I'll see you on Wednesday. And remember, I have office hours if you have any questions. Bye.